About the lab. Since we missed one lab session, we're just going to try to make it through one unknown. So try to finish up your known, and then you'll analyze your unknown. But the known, there's the ammonium test. A number of you have already done that, but it's fairly straightforward. It doesn't take too much time, and it gives you clues as to what your unknown might contain, depending on what the precipitate forms it looks like. So, for example, if you had silver present, you'd expect a dark brown PBT, lead, white, manganese, brown. If you get a mix, then it's hard to tell. But whatever you have for your unknown should be consistent with what the precipitates you might see here. We aren't analyzing the precipitates in this particular test. We're just looking for ammonia gas, which turns red litmus blue. Okay, we're going to analyze your unknown for anions too. We have an anion solution. The anion solution is going to be different than your cation solution. The anion solution is just located on the back lab bench, and it just contains a sodium salt. So it means sodium chloride, sodium sulfate, sodium nitrate. We're going to test for these individually. And so we'll take a portion to test for chloride. And so take a portion of your known mixture or unknown mixture, and then just add some silver nitrate to it. Silver nitrate stains things black, so be careful with it. But silver ions like chloride, and we'll get a white PBT. Nitrate and sulfate don't really precipitate with silver. You need pretty high concentrations of sulfate to precipitate here, so it turns out sulfate won't precipitate under these concentrations. That's a double replacement or metathesis reaction. This is also a double replacement or metathesis, and that is the reaction of sulfate with barium ions. Barium likes sulfate to precipitate out barium sulfate. It's white PBT. And so these two are very fast. If we get a white PBT with silver nitrate, it's positive for chloride. If we get a white PBT with barium nitrate, it's positive for sulfate. Nitrate analysis is a little bit more involved. Nitrate's going to require a redox reaction. And so for the nitrate reaction, we take a sample of unknown or known. It says 3 milliliters. You can probably use less if you want. So we have nitrate aqueous here. And then to this nitrate aqueous, we're going to add FeSO4 solution. FeSO4 is iron 2 sulfate. This should be green. If it's yellow, it's been oxidized to iron 3 rather than iron 2, and it won't work. And so we're going to add this, and these two solutions should mix nicely. So the key ingredients here are going to be nitrate and iron 2 ion. Sulfate will be a spectator. Nitrate's a good oxidizer in the presence of acid. And so what we're going to do is we're going to put in some concentrated sulfuric acid in here, using a little plunger, I think about 2 milliliters. This has an auto dispenser, and it's just like a syringe. You just pull it up and then depress it down, and it auto dispense 2 milliliters of concentrated sulfuric acid. Concentrated sulfuric acid is dangerous. It's dangerous because it can cause severe burns, like 3rd-degree burns. And so, if that's the case, we don't want to hold this with our fingers. We're going to use a test tube clamp to hold then the concentrated sulfuric acid is like syrup. It's really viscous and it's dense. And so when you mix it, you let it go down the side, inside wall of the test tube, and it sinks to the bottom. It's a liquid. Eventually it will mix. But initially it just sinks. And so here we'll have our concentrated H2SO4 aqueous layer. And so what we need for this redox reaction to occur is we need acid. And the concentrated sulfuric acid will provide the acid H+. It's going to occur, the reaction is going to occur at the interface here between the two layers. And so what happens here is we're going to add excess Fe2+, and that's going to convert the nitrate into nitrogen monoxide gas or nitric oxide plus iron 3. The nitric oxide or nitrogen monoxide is colorless gas. It's hard to detect. And so one way of detecting this is by the reaction between nitrogen monoxide gas and excess iron 2+. What happens is the nitric oxide attaches to the iron and it makes this. This is an example of a Lewis acid-base reaction where the Lewis acid is iron 2, the Lewis base is NO, and this is our Lewis acid-base adduct. Our Lewis acid-base adduct, this is aqueous, is a brown liquid layer or brown solution. And so at the interface between the concentrated sulfuric acid and the nitrate H+ solution, we should get, this is the wrong color, but we should get a brown liquid layer. That brown liquid layer is called the brown ring. And the brown ring is just this iron NO 2+ ion aqueous. We call this a complex ion, and those are talked about in Chem 1B. And so what we end up with is this, the FeNO2+, which is dark brown liquid layer or aqueous layer or solution at the interface here. And so we're looking for a brown color. Sulfuric acid is colorless. And this nitrate with the iron 2+ is green, light green color. So it's not a precipitate that we're forming, just a brown layer. If we get that brown layer, then that's positive for nitrate. This test doesn't take very long. The brown layer develops rapidly. Okay, once you test this, we got to tilt the test tube like this. You want to dump it into the waste. You have to watch out because of the concentrated acid. All right, any questions on the nitrate test? No? All right. Normally, when we do this unknown, it's like an unknown exam. And with unknown exams, like this particular one, the way I have people do it is it's closed lab manual, open lab notebook. And so what they need to do is they need to do the whole procedure based on their observations that they wrote. And so if you can repeat the procedure using the observations you wrote, then your observations are adequate. With a lot of people, they don't write enough observations. And so they don't have enough detail to repeat it. Observations, meaning that you don't read the procedure. The observations would be like if you have the flow chart and then some additional details in here. That would be observation. But for this, since we missed one lab day, then it's not going to be so strict. Normally when I do this, unknown exam, you have to work individually. You can't talk to your neighbor, for example, you can't ask them what to do next. You know, you can't ask me what do I do next. You have to figure it out yourself, what you need to do next. That's normal. But in this case, you can talk to your neighbor if you want. You can ask me questions because I'll tell you what's going to happen. What's going to happen is something like this. Your unknown is not going to contain all of these. Let's say your unknown contains barium and manganese. If your unknown contains barium and manganese, you add HCl, will you get any precipitate? Yeah, if you don't have any silver, you're not going to get a silver chloride precipitate. What's the other precipitate we expect here? Yeah. If you don't have any lead, we aren't going to get any precipitate. And therefore, this is what happens typically. One, you add a drop of HCl, nothing happens. You add another drop, nothing happens. Another drop, nothing happens. Should you add the remaining? No, you don't want to add the remaining balance of HCl because what that's going to do is going to interfere with subsequent steps. So if you're not getting any precipitate, after a few drops here, then that means you have nothing to precipitate. If you have nothing to precipitate, then you don't get any precipitate. If you don't get any precipitate, do you still need to wash your precipitate?
No.
Yeah, there's no precipitate to wash. So, one of the questions I get is, I didn't get a precipitate. How am I supposed to wash my precipitate? Well, you can't. You can't. Then the next question is, how do I filter it? Because I didn't get any precipitate. So if you don't get any precipitate, you don't filter, you don't wash, you don't do anything. In fact, you can eliminate this whole branch. If you eliminate this whole branch, you know how much time that saves?
Yeah.
That saves a lot of time. And so because our unknown doesn't contain all these ions, it goes a lot faster than your known. Because your known, you had to do all the steps because you had all the ions. But your unknown, you can skip this entire branch. If there's no silver, there's no lead, there's no reason to do this. There's no reason to add all the HCl that they tell you to add. If you had just silver, you get a precipitate here, and then you try to dissolve it in hot water, maybe it looks like nothing changed. And so, you would have no lead here, but you'd still go through the motion if you had lead. If you had lead here, then it should all dissolve. If there's no silver, all lead, you get a white PPT, which dissolves in hot water. Brings it over here. Unfortunately, what some people do is they don't dissolve. It's like dissolving sugar cubes. It doesn't instantly dissolve. It takes a little bit of work. You have to crush up the sugar cubes to get them to dissolve. The same thing here. It's not like you heat. If this were lead 2 chloride, it's not like you heat this and it all dissolves. You have to crush up the crystals to get them to dissolve. So sometimes what people do is they have no silver and they have lead. And they get a precipitate over here, but they don't dissolve that precipitate. And then they add the sodium hydroxide. And what happens is when you add sodium hydroxide to lead chloride, you end up with white. And so you go from white PPT to white PPT. So if somebody asks, what happened? What do I do next? And so what happened was they didn't quite get a clean separation. What we're trying to do is get clean separations. And usually this happens. So normally what happens is people get some bizarre colors or bizarre results. But it's probably because previous separation didn't work so well. So they should go back. Other parts are, if you don't get a precipitate here, then it doesn't save you much time. But anyway, for your unknown, you aren't going to do all the steps. And if you don't do all the steps, then the easiest way of seeing what to do next is via the flow chart. Because if you follow the procedure, typically when you follow the procedure, you just want to go step by step by step. But it's not going to work. because you'll have to jump. And then where do you jump to? Well, I get a lot of questions like that. If you have something like this already kind of mapped out, then it's easy to see where you're going to jump to. All right, so that's for tomorrow. I'm not going to talk. We're just going to straight into lab. That way you have the maximum amount of time to work at finishing your known and then trying to do at least one unknown. When you get to your unknown, you're going to test it for both cations and anions. And so when you get your unknown, you have to make sure you have enough solution to test. And so you need 12 milliliters for this. And so you need more than 12 milliliters of unknown. You need 3 milliliters, 3 milliliters, 3 milliliters, 3 milliliters. So that's another 12 milliliters. So altogether, we need 24 milliliters of unknown in order to conduct all the tests. So they're probably going to give you more than 24 milliliters. Don't use all 24 milliliters for one test. Sometimes that happens. Somebody will use an entire unknown sample just for testing for ammonium. Okay. This equation I didn't balance. We'll talk about how to balance these in chapter 19. Were there any questions on the homework? No. Where did I leave off last time? Okay.
So we know what we end up and what we might.
On the practice test, you're saying?
Yeah.
Which one was that?
We didn't go specifically into this for example, probably for
Like this one here?
Is there like somewhere in the homework that we could
This one, yeah, there are some that are similar. This is 7.00% mass HCl. So this is solutions, but the first time was back in earlier chapter. There was a problem. I think one. It was the mixture problem. It was in the stoichiometry chapter. Basically, if we look at the stoichiometry map, we have grams of A to moles of A, then moles of A to moles of B, and then moles of B to grams of B. But sometimes we're not given pure A. Sometimes we're given grams of mixture containing A. And then if we're given grams of mixture containing A, then we need the percent by mass composition. Or sometimes we're given grams of B, but we don't want grams of pure B. We want grams of mixture containing B. And again, here we'll need to know the percent by mass composition. We'll have to flip it over though. And so the first time that came up, was in chapter 10. So like number 75 here would be like this. I don't think I did number 75 though. I think I did this one, number 76. So 75, 76, 77, 78, 79. Yeah. I think that's it. Those would be good. This is chapter 10. And, those would be very similar to the problem on the test. Now, the problem on the test wasn't chapter 10. The problem on the test was the aqueous mixture solutions. But there are different units that you could use for solutions. Percent by mass composition is one. Molarity is another. So that's fine. Yeah. So it would be 75, 76, 77, 78, 79. Those are all percent by a mixture, either going from mixture to pure A or going from pure B to mixture B. This is what I was saying earlier about the stoichiometry math missing some branches. You know, when they did the stoichiometry map in the later chapter, they didn't show these branches with the mixture. And so that's why. Okay. Other questions? Uh-huh.
I should have one. In 16.3, you probably went over it unfortunately. In like online format, I don't comprehend well. Um, but it says water is capable of dissolving more than its own mass of some solids. The water continues to be called a solvent. Why wouldn't water be a solvent if something is dissolving into it?
Where did it say that?
At the beginning of 16.3 solution terminology, solute and solvent.
Okay, so your 16.3 is probably my 16.2. We'll look at that. All right, when solids or gases are dissolved in liquid, the solid or gas is said to be the solute, and liquid is the solvent. More generally, the solute is taken to be the substance present in relatively small amount. The medium in which the solute is dissolved is solvent. The distinction is not precise, however. Water is capable of dissolving more than its own mass of some solids, but water continues to be called the solvent. In alcohol water solutions, either liquid may be more abundant, and in a given context, either may be called the solute or the solvent. So, usually it happens for things like HCl. HCl is a gas, and you can dissolve that in water. When you form as HCl aqueous. HCl aqueous, the solute, is hydrochloric acid or hydrogen chloride, and the solvent is usually water here. And what we can do is we can have it from low concentration to very high concentration. If we go to a very high concentration, let's say we go to 12 molar HCl. If we go to 12 molar HCl, then there's more HCl in terms of mass. HCl is heavy because chlorine is 35 grams per mole. So it's fairly heavy. And so this contains more, but since we have a range, we can go from 0.1 molar or smaller to 12 molar to 18 molar. HCl. Since we have the range, it's inconvenient to flip it. Once it becomes more HCl by mass, we'd like to flip it, HCl, the solvent, but there's two problems with that. One is HCl is normally gas, and so that wouldn't qualify as a solvent. And so those are different cases. And two, it's just a matter of convenience. If you've been calling H2O the solvent, you just continue to call it the solvent all the way across. I wouldn't worry too much about this.
It just confused me. I didn't know this because I was reading it incorrectly or the way it was worded.
No, it is confusing. It's confusing because in the second part they say flips. I wouldn't worry about it. It wouldn't be wrong. I mean, if you flipped in certain moments. Okay, were there other questions? All right, where did I leave off last time? Did I talk about pH? Did I talk about this reaction between two water molecules? pH 7? No? Did I talk about Lewis acids bases?
No, yes, about, they said that, Lewis acids and bases can describe all five elements.
Okay.
Arrhenius is usually livid, and gold is still more than.
Yeah, so Bronsted the most useful for us. Yeah. Bronsted the most useful for us. Yeah. And we can rank the acids here. These are all Bronsted acids here. These are also all Lewis. But there's no simple ranking for Lewis acid base because it depends on multiple factors, the bases. And so for Bronsted, we get this simple ranking chart here of 7 common strong acids, some strong bases. Did I talk about base hydrolysis, aqueous ammonia? I talked about precipitating hydroxides? No?
I don't do Zoom well.
Spoke about more hydroxide and how it's difficult to disassociate in solution.
Okay. Yeah. I think I'm pretty sure I talked about the bases. All right.
The last thing I remember seeing was teeth, if that helps at all.
Last time you saw were teeth?
Yeah, there were teeth on the Zoom screen. I think you were showing like some type of, I don't know. I just remember seeing leaves and I remember seeing teeth. If that helps at all.
Yeah, I think so. I think I was talking about metabolism. I was talking about hydrofluoric acid. You know, is hydrofluoric acid a weak acid or a strong acid? It's a weak acid. The situation is hydrochloric acid. I haven't spilled any 12 molar, but I've spilled 6 molar on my hand. 12 molar would burn. Okay. And I've spilled lots of 0.1 molar HCl is no big deal. I've spilled lots of 0.1 molar HCl on my hands. Doesn't burn. It's bad. Even 6 molar is not that bad. But, and hydrochloric is a strong acid. But, you know, if it came to hydrofluoric acid, I'd never want to spill any hydrofluoric acid on my hand. Right? Because even though hydrofluoric acid is weak acid, it doesn't burn that much. It would result in excruciating pain. Does anybody recall why or what happens with hydrofluoric acid? Well, actually both. Hydrofluoric and hydrochloric are both oxidizers because they both contain H+. H+ is an oxidizer. And so as far as oxidation, they're somewhat comparable. You know, it's not the redox properties. It's not the oxidation. It's not the acid-base properties because if it were acid-base, then hydrochloric is stronger. It's the what properties of hydrofluoric? This is why I was on the T. It's the yeah. So the point I was trying to make there is hydrofluoric acid is dangerous not because of its acid base, not because of its redox. It's dangerous because of its metathesis properties. You know, fluoride loves certain cations. One of the cations fluoride loves is calcium. Fluoride loves calcium, and what forms is calcium fluoride to precipitate. And so people do that. They brush their teeth with sodium fluoride. The fluoride replaces hydroxide in calcium. I mean, in the calcium containing. It's a lattice in your teeth, calcium hydroxyapatite. And that helps strengthen it, because if you can replace hydroxide with fluoride, it makes it more resistant to attack from acids. But the problem with hydrofluoric acid burns is this. If you spill some on your hands or arms, you want to get rid of it as soon as possible. You wash it off. Because what happens is it doesn't really burn, but it will penetrate your flesh. And as it penetrates your flesh, eventually it'll hit bone. When it hits bone, then it starts to precipitate out calcium fluoride. You think precipitating out calcium fluoride, no big deal. But apparently it's a big deal because apparently it's extremely painful when your bone starts precipitating out calcium fluoride. So at the electrical engineering, I was talking about the electrical engineering department, the wall of horrors. Was I talking about that? On the wall, they have a calcium chloride injection kit. So if you do spill some hydrofluoric acid on you, you're supposed to inject yourself with calcium chloride. The calcium chloride goes into your blood and hopefully precipitates out the fluoride before it hits your bone. Something like that. What's that?
Yeah, hopefully.
Hopefully, yeah, right. Right, in time, right. Something like that. Yeah. So we look at all the properties. We look at acid, base, redox, and metathesis when analyzing. Here we're just looking at acid base. Now, when we look at acid base, we should look at Lewis acid base reactions because Lewis acid base is the most comprehensive definition. But sometimes analyzing Lewis acid base reactions is difficult, like this. What's happening here. But when you get more practice with these, then it's easier to recognize. But when it comes to Bronsted acid base, it's always easy because Bronsted acid base are always the same thing. When you have a Bronsted acid, it's always H. All Bronsted acids begin with H. Okay. Bronsted acids are proton donors. Bronsted bases are proton acceptors. And so predicting Bronsted acid-base reactions is simple. When we predict it, first we got to recognize, is it an acid or base? So we look at these. This is hydrogen oxalate or bioxalate. Ammonium is phosphoric acid. All these are acids here. Some of these are bases too. Like hydrogen oxalate occurs on both sides of the chart. And so it's both an acid and a base. If it's both an acid and a base, it's called amphoteric. And so if I look at this, I find hydrogen oxalate on the base side over here. And then I find hydrogen oxalate on the acid side here. And sometimes it's heavily biased one way or the other. So for example, hydrogen oxalate appears to be a better acid, because it's mid-pack, than it is a base. Base is borderline extremely weak. Some of these amphoteric species are equal. So for example, water. Water is pretty weak as an acid, but it's also pretty weak as a base. So both of these are. Water can go either way. And so in this particular problem, all we do is rank this based on the chart. So we look at hydrogen oxalate, ammonium, and phosphoric acid, and see which one's the strongest, which one's the weakest. So we want the strongest first. So we go to the chart and take a look. Start off with the strongest. First one we hit is phosphoric. Next one we hit is hydrogen oxalate, and the last one we hit is ammonium. And so the strongest first would be phosphoric acid, followed by hydrogen oxalate, followed by ammonium. This problem, you just use the chart to rank it. And so they just use the chart, figure 1760, right? Did I talk about predicting acid-base reactions?
No.
No.
I do have a question. I forgot to ask during the class last time.
Mhm.
Do we have access to the PowerPoints? Because when I tried to look at them to like take notes and stuff, it wouldn't let me access them. So I don't know if that's a teacher only like source. Because I think it's like the same thing as the book, but I think the presentation just helps me a little bit more. I just don't think we have access to it.
You should have access to it.
Yeah, we do.
You don't?
Yeah. You want to try doing like student view, maybe? Because it's in the discussion. Yeah, maybe if you want to do like student view and see.
Is this what it looks like?
Yeah, but when we click on it is when there's the problem.
Yeah, this is.
Yeah, that's why I said if you look at student view, maybe you'd see.
Did you click on the link?
Yeah.
This download.
Professor, it's that's what it looks like.
Access denied. You don't have access to view this resource unauthorized.
Yeah, it doesn't look like it's something on your end. I'm not sure how it would be.
You don't have access to. Did everybody get that? Access is denied?
Yeah.
I think they must search the copyright here. Maybe? How come I can do this? Do you guys want the PowerPoint?
Yeah.
And nobody in the morning said anything about it, so that's weird.
Yeah, I don't know if they. Maybe they just didn't care.
All right, see if you get that email. No. Acid-base reactions. I'm going to do a little bit different than what they did here. Let's just take a look. Well, there are two methods. Did I talk about this? Did I talk about the zigzag versus charm method? No? I'm calling it zigzag method, but that's probably not its formal name. This is the zigzag method here. No, zigzag, zag. Zigzag, zag, it's not that. Let's do the chart method first. HSO4 minus plus OH minus. This is it here. For the chart method, what we do is we identify these as acids and bases. So the first one we look for is HSO4 minus. And so we consult the chart here and look for HSO4 minus. And I see it here. But what you have to be careful of, you have to be careful of things that occur on both sides of the chart. And so HSO4 minus is one of those. And so this one occurs on the acid side of the chart, so I'll label it A, acid. Did I talk about conjugates? For example, these bases here, the conjugate bases of the strong acids are so weak that we don't even consider those bases. Yeah. Well, HSO4 minus is a base here. And it's such a weak base, we don't really consider it a base. But anyway, I'm going to label it a base here because it occurs on both sides of the chart regardless. And so HSO4 minus can act as an acid or can act as a base. In other words, HSO4 minus can donate a hydrogen ion or can accept a hydrogen ion. That would be HSO4 minus. Hydroxide we know is a strong base, like sodium hydroxide, a strong base. But hydroxide is also one of those weird things. Hydroxide is a strong base here, but it's also a terribly weak acid. It's a much better base than it is an acid, but since it occurs on both sides of the chart, we're going to label it both an acid and a base. It's an acid because it can lose an H+. If hydroxide loses an H+, what does it form? If hydroxide loses an H+, it forms oxide. Oxide is an even more powerful base than hydroxide. There's one more species in here. Do you know what the one more species is? Well, there has to be some cation in there. Oh, let's take a look at the original column. The original column, they aren't telling us. We just have to assume the cation is unreactive. And all of these are aqueous. So do you know what that one more species is? The one more species is water. Water occurs on both sides, so it's amphoteric. And so all three of these species can act as the acid. All three of those species can act as a base. If all three can act as the acid, are all three going to act as the acid? No, do you know which one's going to act as the acid? The strongest one. And so in the chart method, we identify and then we pick the strongest acid out of these three. Well, picking the strongest acid out of those three, we just consult the chart. And so which one is the strongest of those three? Well, certainly not hydroxide. Hydroxide is at the very bottom of the acid. It looks like it's going to be bisulfate, because water is not much better. If you look at hydroxide, it's here. Water is a little bit better than hydroxide. And then HSO4 minus is a lot better. HSO4 minus is actually borderline strong. It's pretty decent. Uh-huh.
The HO4 minus, do we get that hydrogen by being protonated by hydroxide, or from citric acid?
Well, yeah, there are two ways to make HSO4 minus. The two ways we can make HSO4 minus is HSO4 minus can be made by deprotonating H2SO4. So we remove an H plus. Or it can be made by protonating an SO4 2 minus.
Does it get that H from in this equation, or we get it from the bottom? And that's why it's considered base.
This H?
Yeah.
This H is already attached to it. HSO4 minus is, we get this HSO4 minus by taking sodium sulfate. Actually, let me give you a more realistic problem than this one. This comes from, let's mix sodium bisulfate and sodium hydroxide. So if I take sodium bisulfate and sodium hydroxide, what do I expect to form here? Well, this looks like an AB plus CD, double replacement. If it's double replacement, what am I going to form? I'm going to form sodium hydroxide and sodium bisulfate. And so in terms of double replacement, there's no reaction for double replacement. But double replacement isn't the only type of reaction we look for. What other types of reactions do we look for?
Maybe a redox one?
It could be a redox reaction, or it could be a acid-base. It turns out it's not redox in this case, but it's acid-base. So if it's acid-base, the first step in the chart method is we inventory. So this is step A. Call it inventory. If I inventory, I have sodium ions. I have bisulfate. Now, bisulfate doesn't lose that hydrogen easily. It's a weak acid. Weak acids only partially ionize or hydrolyze or dissociate. And so this pretty much stays intact. We have hydroxide and we have water. Then we ladle everything. Sodium ions don't have any hydrogen to give up. They're not acidic and they don't accept hydrogen. And so these are neutral. Bisulfate's an acid base, hydroxide's an acid base, and water is an acid base. Then we pick the strongest acid. The strongest acid is going to be bisulfate. And which of these three will be the strongest base?
The hydroxide.
The hydroxide, yeah, looking at the chart. And so the acid-base reaction is going to be this. And so A, we inventory, then B, we choose the strongest acid and base. C, we react by transferring one proton from the acid to the base. And so this is the acid, this is the base. we could have gotten it backwards. We could have transferred the proton from hydroxide. But that reaction is less favorable than this. So we're going to transfer the proton, therefore we're going to be left with sulfate, protons H plus, in water. D, determine driving force. Driving force is going from stronger to weaker. In this case, it's going to go from stronger to weaker acids and bases. So if we look in the forward direction, that's our acid and our base. If we were to reverse this, then who's losing the hydrogen? Water is losing the hydrogen, so this will be the acid. Sulfate is gaining the hydrogen, so this will be the base. These would be conjugate pairs. So bisulfate and sulfate are conjugate pairs, and hydroxide and water are conjugate pairs. But anyway, what we're going to do is we're going to compare the two acids. Which one's a stronger acid? Well, it turns out bisulfate is going to be a stronger acid based on the chart than water. Which one's a stronger base? Hydroxide is going to be a stronger base than sulfate, which is a weaker base. And so we have driving force present. We're going from stronger acid, stronger base, to weaker base, weaker acid. And so we expect this reaction to occur. So this would be the Bronsted acid-base reaction. In other words, weaker acids and weaker bases are less reactive, more stable. And so this is a downhill reaction in this case. This is downhill in terms of energy. Okay. So that's the chart method. The zigzag chart method. Bisulfate, this is the acid we're reacting here. That's here. The base we're reacting is hydroxide. That's here. So we're going to take bisulfate and react with the hydroxide. That's our zinc. So the bisulfate reacts with hydroxide. This is our base. This is the zinc part. Usually we say the base attacks the acid. That's fine too. Hydroxide attacks the acid. All right, when bisulfate reacts with hydroxide, this is our ZAG part, then the bisulfate is converted, the hydroxide is converted into water. That's our ZAG. So bisulfate reacts with hydroxide. Hydroxide gets converted to water. And then bisulfate gets converted into sulfate. So here's our driving force. Our driving force is, this is downhill. We're going from stronger acid uphill to weaker acid downhill here. So this is driving force. Now the bases are flipped upside down. The strong bases are located at the bottom and the weak bases are located up higher. So this is downhill in the opposite universe, the base universe. This is downhill. So over here we're going from stronger base to weaker base. So what we want to do here is we'll just look at acids. If we just look at acids, then what we want to do is we want to go downhill here. And that is we're going from bisulfate to the weaker acid, water. that is a stronger acid, bisulfate, and weaker acid, water. And so we could use this method for all of these. This would be favorable. In fact, if we take bisulfate, we could react it with any of these bases. So for example, if we take bisulfate and react it with the base dihydrogen phosphate, this would be our zig, then dihydrogen phosphate would go to phosphoric acid. Well, that's downhill because bisulfate is a stronger acid than phosphoric acid, so we're going downhill. And then the bisulfate's converted into sulfate. And so what we're going to end up with is the weaker base, sulfate, from the stronger base, dihydrogen phosphate. So this would be downhill. So bisulfate reacting with any of these bases here will result in reaction. But if we try to react bisulfate with hydrogen oxalate, that would be uphill. Because if bisulfate reacts with hydrogen oxalate, that would be unfavorable. So let's take a look at that. So let's say we go through and the reaction is bisulfate reacting with hydrogen oxalate. Ion. Here. So bisulfate's the acid, hydrogen oxalate's the base. And what's that going to form? It's going to form oxalate, or is it? What is it going to form? Not oxalate. Oxalic acid. And sulfate. So in this reaction scenario, this is uphill. So we're going from a weaker acid to a stronger acid. That's not favorable. And so there's no driving force. And then likewise over here, we're going from a weaker base to a stronger base. This is not favorable. And so when we're looking at the zag part, this is the zig part here, the two zags are unfavorable here. Whereas when we look at this part, the zig part here, the two zag parts here are favorable. These are downhill. This is going downhill here, and downhill is actually uphill on the right side. Whereas this is going uphill, that's not favorable. And so we could use this method to predict all reactions. So why don't you try one of these? We'll try this example that they give in the PowerPoint. They make this a little bit easier because there aren't that many species. They just want the reaction between HF and sulfide ions, hydrofluoric acid and sulfide. So HF and SO3 2 minus. So one, if HF reacts with SO3 2 minus, what forms? So this is the zig. What's going to form? What's going to form is this. Bisulfide or hydrogen sulfide and fluoride. Is that favorable or not favorable using the zigzag method? So if HF reacts with sulfite, it's going to form HSO3 minus. So we're going from stronger acid to weaker acid, which means it's favorable. That's downhill. It's driving force. So we expect a reaction to occur.
Is there any significance between which lines are solid and which lines are dotted? Because I see they switch in both equations. Or does it just matter on which one you should understand?
I don't. I think I just switched it by accident. The dotted.
Yeah, because the dotted lines went,
Vertically.
Oh, vertically. And did I keep these as solid here?
yes.
Yeah, this would be the dotted here. It would be dotted here. Just the inconsistency on my part. Let's try this one. HF with sulfite. Actually, what I was trying to do is this is the zig and then the zag parts here. So I was trying to do the zags as dotted. So this is the reaction, and then these are the products. HSO3 minus and chloride. So here we're going downhill. We're going from stronger acid to weaker acid. So the overall reaction is HF plus SO3 2 minus yields F minus plus HSO3 1 minus. And then we're going from stronger acid, HF, to weaker acid, HSO3 minus, and this is our driving force. If the acids follow this, then the bases follow the same trend. Okay, that's the zigzag method. The chart method would be something like this. The chart method would be HF plus sodium sulfite yields what? And so it would be a little bit more complicated. As first, what would we have to do? Inventory. So we're going to have HF. HF is a weak acid, leave it alone. But sodium sulfite is a strong electrolyte, so we break it apart. There'll be sodium ions and sulfite ions. And then there's one more thing that's missing. And that will be water. And then we use the chart to label. HF is only an acid, it's not amphoteric. Sodium ions are neutral. Sulfite ions are only a base. Water is both an acid and a base. Then we pick the strongest acid, which would be what? Yeah. Strongest acid would be hydrofluoric. The strongest base? Water is a pretty weak base. So sulfite is a much stronger base. And then we react these two. The acid loses a proton, the base gains that proton. And so we're going to end up with fluoride plus HSO3 minus. Then we reverse this in C. So we have the acid and the base in the forward direction. In the reverse direction, fluoride's got to be the base, and bisulfite or hydrogen sulfide has got to be the acid. And then we compare the two acids. HF is a stronger acid. HSO3 minus is a weaker acid. Then we have driving force here. So the chart method is good for individual reactions. And we're given some specific things. The zigzag chart method is good for general chemical properties. And so for the zigzag method, we can answer questions like this. What bases will HF react with? What bases HF reacts with will all be downhill. So what bases will be anything stronger than fluoride? In fact, all bases stronger than fluoride will react with HF. Like nitrite. Nitrite's stronger than fluoride. So this would be our zig, and then our zag forms HNO2, which is a weaker acid. And our other zag forms fluoride, which is a weaker base. HF reacts with this one. This one is formic acid, so this is formate. This one, you don't have to know the name. What? And so all these bases, HF will react with. And so in terms of chemical properties, what we say is HF reacts with all bases stronger than fluoride. However, will HF react with any base weaker than fluoride? No. It's not going to react with any base weaker than fluoride, because if HF reacts with H2PO4 minus, what's going to form is H3PO4, which is a stronger acid. So we're going from weaker acid to stronger acid. So any base that's above fluoride is weaker, and all these weaker bases will lead to a stronger acid, which is going to be unfavorable. And so, for example, HF will react with nitrite. However, will HCl, hypochlorous acid, react with nitrite? No. Hypochlorous acid will not react with nitrite. That's uphill. Hypochlorous acid will react with any base that's stronger than hypochlorite, but it will not react with any base weaker than hypochlorite. And so that's the utility of the zigzag method. Zigzag method, we can more broadly indicate what the chemical properties are. Then some similarities, like, for example, acid-base, Bronsted acid-base involves transfer of protons. Redox reactions involve transfer of electrons. So there's some similarities, but just in terms of protons versus electrons, I'm not really going to talk much about that. How about this reaction? Is this a favorable Bronsted acid-base reaction? Let me show you this in structures here. We have two waters, and one of these waters we're going to label the base, the first one, and the other water we're going to label the acid. And so the acid donates a proton to the base. So in other words, what typically, the way we visualize this is more in terms of Lewis. The base attacks this. So this lone pair gets pushed into here, so it converts this lone pair into bond, and it breaks this one here. And so what we end up with is this, H3O plus which is hydronium, and OH minus, which is hydroxide. And then we compare the driving force. If we go backwards, this will be the acid. Hydronium loses a proton. And this will be the base. This gains a proton. And then we compare what's a better acid, water or hydronium? Hydronium. Water's weaker. What's a better base, hydroxide or water? Hydroxide. So this reaction is unfavorable. Hydronium and hydroxide are strong acid, strong base, and they're very reactive. And so when we look at this reaction, overall this reaction is very energetically unfavorable. H2O plus H2O liquid is uphill. It's going to form H3O plus and hydroxide. It's uphill. And so in terms of the zigzag method, we look at it like this. Our acid, H2O, reacts with our base, H2O. So that's the zig part. The zag is we're going to form hydronium. And so let's compare the strength of water versus hydronium. Hydronium is a much stronger acid than water. So this is really uphill. That's what I'm trying to illustrate with this. This is really uphill for both. Because if water reacts with water, we form hydronium, and then this water gets converted into hydroxide. So this is very uphill too, because we're going from water's original base to hydroxide. Well, since this is inverted, the base side's inverted, this is very uphill in terms of both the acid and the base. And so it's very unfavorable. And so what we say is that the driving force is in the reverse direction here. But this particular reaction can actually happen at room temperature. That's because of this. Not all the water molecules have the same energy. Do you recognize this curve? What's the name of this curve? It's a curve that plots population on the y-axis and the kinetic energy on the x-axis. Somebody remember the name of this? The Maxwell-Boltzmann distribution. And all this says is that 25 degrees C, not all the water molecules have the same energy. If I had 1 billion water molecules here, then most of these will stay down here at the bottom of the hill. Out of that billion, how many can make it to the top of the hill? Well, it depends on how high of a climb that is. This is a very steep and long climb. So if I had 1 billion, it turns out, in my population of 1 billion, only about 4 of them have enough energy to make it to the top. And so this is the energy that's required here to climb to the top of that. And then that's only about 4 out of 1 billion. 4 out of 1 billion is what we call negligible, right? In fact, if there's only 4 out of 1 billion, you just ignore it. It's negligible. But for this particular reaction, we worry about this. This is an example of a equilibrium reaction or reversible reaction. This reaction can go in two ways. It can go up, which is unfavorable, and it can go down, which is highly favorable. The reverse direction is highly favorable because we're taking a strong acid and a strong base. A strong acid and a strong base react to make weak acid, weak base. That's highly favorable. This is really downhill. So there are two ways to show this. The two ways to show this. One is that we take a ratio. No. Because what we're showing here with these two arrows is it can go either way. But it doesn't show us which way is favored. To show us which way is favored, we draw things like this. We draw a small arrow going forward and a big arrow going backwards. And so this shows the forward direction is very small, and the reverse direction is very big. Or we show this using K. K is something called the equilibrium constant. The equilibrium constant is a ratio between the products over the reactants. So if K is big, then it's all products. If K is small, then it's all reactants. So those are two ways that we show this. For this one, the K is known. The K we call KW. This is the water constant, or water equilibrium constant, is 1.0 times 10 to the negative 14. That comes from the product concentrations over the reactant concentrations. Put that in here, concentration. And so this is going to equal the H plus, or the hydronium, times the hydroxide concentration. That's a very, very, very small number. And that means we have very little H plus or hydronium. I'm using H plus and hydronium interchangeably. And very little hydroxide. In fact, we could do this. It turns out that the hydronium and hydroxide have to be equal because stoichiometrically, we make equal amounts of both. And so it turns out that the hydrogen ion concentration is 1.0 times 10 to the minus 7 molar, and the hydroxide ion concentration is 1.0 times 10 to the minus 7 molar. We can actually measure this. We can actually measure this using pH meter. The pH meter measures the power of the hydrogen ion concentration. If I look at it, it's actually the negative power. The power of the hydrogen ion concentration is negative 7. And so what I'm going to do is I'm going to change the sign and call it pH 7. This is actually pH 7. This is going to be pH 7.00. We can also do the same thing for the power of the hydroxide ion concentration, POH. The POH is equal to 7.00 here. So basically, we have an uphill reaction. This is a terribly uphill reaction. And usually, if we're just looking at the driving force, we say there's no driving force for this reaction. And we ignore it. If there's no driving force, we don't expect much reaction to occur. How much reaction? A negligible amount of reaction occurred. This is negligible. But that negligible amount of reaction gives water its pH. Otherwise, pure water shouldn't have any hydrogen ion in there. Pure water should just consist of water molecules. But in pure water, there's this tiny, minuscule amount of hydrogen ion, which gives us a pH of 7. It's 10 minus 7 molar, which is 0.1 micromolar. Very, very small. And so normally a reaction like this we don't really worry about. But in this case we're going to worry about it because of pH. pH is an important quantity we measure in water. And so we'll talk more about this. We'll go on a break right now. We'll start up again after the break. This reaction is termed an equilibrium reaction. It's a dynamic equilibrium because you're never going to stop having collisions that are forceful enough that you generate some hydronium hydroxide. But when the hydronium and hydroxide come into contact with one another, they immediately react to drop back down to water. And so what we end up with is a stable concentration. The stable concentration is about 4 out of a billion, are always up there. That's not always the same 4, it's always interchanging. So we're going in circles here. But the bulk of the population's down here, and then a tiny fraction of the population's up here. But it's stable. So this is an equilibrium reaction. An equilibrium reaction is dynamic. This is called a dynamic equilibrium. It's dynamic because the collisions, you can't stop the collisions. Collisions are always going to happen. Whether they're between 2 water molecules or hydronium and hydroxide, those collisions are always going to occur. What the equilibrium part is, the EQ part is, we've reached a state where the forward reaction rate is equal to the reverse reaction rate. And so drawing 2 equal arrows like this is fine. So in this dynamic equilibrium, we have a stable concentration. The power of that is going to be 7. So this is pH 7. And so water has a pH of 7, pure water. What's going to happen if I change the temperature? What does that do to the Maxwell-Boltzmann distribution here? If I increase the temperature, what will happen to the distribution? Yeah, it kind of flattens, but it shifts to the right. When it shifts to the right, it increases the population here. So at higher temperatures, I'm going to expect a greater population. If I expect a greater population, that changes the pH. So pH is temperature dependent. But that's a hassle because then we need to know that what is the pH of pure water at different temperatures. Do you want to have to know that? No. And so the easier thing to do is just keep the pH of pure water the same. And so if I change the temperature, it's going to shift the population one direction or the other, which is going to change the concentration here. But in order to prevent that from shifting, we use electronics. And so what the electronics will do is they're going to keep the pH of pure water 7 under all temperatures, regardless if the true pH is actually changing. And so the pH of pure water is 7. When we have a pH of 7, that means the pOH is 7, and that means that the H plus, or hydronium concentration, which we use interchangeably, is equal to the hydroxide concentration. If that's the case, we call it neutral. Because in pure water, we have strong acid and strong base present, just in minuscule quantities. Now, how much is present? How much is present is this. Is pure water a good conductor, or non-conductor of electricity? Non-conductor. And so what that means is that even at this pH here, even with these hydronium hydroxide, 4 out of a billion isn't enough to carry in currents, to give you a current. And so it's an insulator. Pure water is an insulator. This is such a minuscule amount. But that minuscule amount can be measured, and that's what gives us our pH. Now, what we can do is we can take this and upset that balance. That is, we can add acid. If we add acid to this, it bumps up the hydronium. If we bump up the hydronium, well, that's going to create a higher concentration of product, which cascades down. So the more hydronium we have, the more it's going to attack hydroxide. The more it attacks hydroxide, the more reverse reaction we have occurring. And so if we add acid here, acids are going to have higher hydronium concentration than hydroxide. But this is a seesaw relationship because this is a constant at 25 degrees C. And so if the hydronium concentration, the H plus concentration goes up, the hydroxide has to go down. In other words, if the pH goes down, because it's an inverse relationship here, if the hydrogen ion concentration goes up, the pH is going to go down. As the pH goes down, the pH has to go up. Because it turns out that the pH plus the pOH have to add up to 14.00. 14.00 is called the pKW. P stands for power functions. That's what we have here. And so acids are going to have hydronium concentrations greater than hydroxides. Basic solutions are going to have more hydroxide than hydronium. Both acid solutions, base solutions, and neutral, pure water have hydronium and hydroxide. It's just the ratio we're going to duplicate or basic. So let's take a look at number 37. Of what significance is the very small value of 10 to the minus 14 from kW, the ionization equilibrium constant for water? Well, kW tells us the ratio of products over reactant. And so 10 to the minus 14 is very small, which tells us we have very little product. It's all water. That's the significance. And so small ratio means very little product. 38. How is it that we can classify water as a non-conductor of electricity and yet talk about the ionization of water? Well, if it partially ionizes, weak electrolytes partially ionize. Strong electrolytes completely ionize, and non-electrolytes don't ionize at all. And so the amount of ionization that occurs here, that is the amount of reaction, acid-base reaction that occurs here, is so small that it's better classified as a non-conductor than rather than a weak conductor of electricity. So if we have like a weak acid, weak acids are weak electrolytes, there you're going to get a lot more electric conductivity than something like that. 39. The H plus is equal to 10 minus 5 molar. Okay, if the H plus is 10 minus 5, the pH is 5. And the OH minus is 10 minus 9 molar. The pOH would be 9. So the pH is 5 plus the pOH is 9 gives us 14. So pH plus pOH gives us 14. Or the H plus times the OH minus. The H plus times the OH minus is equal to 10 to the minus 14. So that's 10 to the minus 5 times 10 to the minus 9 is 10 to the minus 14. We have exponentials. Is this solution acidic, basic, or neutral? Which one's bigger, the H plus or the OH minus? Or higher concentration? Which one has a higher concentration? OH minus? OH minus, well, maybe if we wrote it in decimal form. Because in decimal, 10 to the minus 9 is going to have 8 zeros. And then a 1 molar. So this is the OH minus concentration. We use square brackets usually to show it. And the H plus concentration is 10 to the minus 5, so it's 4 zeros and 1 molar. And so 10 to the minus 9 versus 10 to the minus 5. 10 to the minus 5 is going to be bigger. If 10 to the minus 5 is bigger, then that means it is what? Bigger, more acid, so it should be acidic. How do you know? Well, whichever one's bigger, that's how you know. 40, an aqueous solution has a hydrogen ion concentration of 10 to the minus 4 molar. So the H plus concentration is 10 to the minus 4, which means the pH is 4. If the pH is 4, what is the pOH? If the pH is 4, the pOH is 10. that means this must be acidic. And so, what is the hydroxide concentration of the liquid? Hydroxide concentration is going to be 10 to the minus 10. We're not really going to do any calculations for pH. It'll be 10 to the minus 10 according to this equation. Is this solution acidic, basic, or neutral? It's acidic. And so what we do here for this is we just look at this chart. Oops, not that. We just look at this. So pH of 7 is neutral. pH is lower than 7 have higher concentrations of H+. And so these are all acidic. This goes by factors of 10. If we, because of this power function. If we go above 7, they're all basic. We go lower concentration. And so, for example, if the pH is 7, the pOH is going to be 7. It's not shown here. If the pH is 6, the pOH would be 8. If the pH is 5, the pOH would be 9, etc. So we could look at it in terms of H plus and OH minus as well. And so what we should know is that here, close to 7, but below is weakly acidic. And then down by 0 is strongly acidic. And then about 8 to about 10 is weakly basic. 11 to about 14 is strongly basic. Some things. Pure waters, pH 7 and 25 degrees C. Blood is slightly basic. Milk is slightly acidic. Sodium bicarbonate solution, slightly basic. Black coffee is slightly acidic. Tomatoes are acidic. Borax is basic. Milk and magnesia is pretty good base. Detergents. Vinegar, pretty good acid, etc. Bleach is a good base. Sodium hydroxide is a great base. Lemon juice, stomach acid, battery acid, they're all strong acids. We can measure the pH pretty easily using pH papers or pH meters like this. We can determine what the H plus concentration is. But because of the seesaw relationship, any pH is less than 7 will be acidic, any pH is greater than 7 will be basic. All right, maybe in the homework I give you some calculations. We could look at some simple calculations. What are the pH, pOH, hydroxide, and H plus of 0.01 molar sodium hydroxide? So this is 0.01 molar sodium hydroxide. That's 10 to the minus 1, 10 to the minus 2 molar. 10 to the minus 2 molar sodium hydroxide would be pOH2. pOH2 means the pH is 12. pH of 12 means that H plus is 10 to the minus 12 molar. And so we could do some calculations like that. You would do the calculations using the equations, but I'm not going to test you on the calculations. You might have to do some for the homework, but you don't have to memorize any of the equations. When we have coefficients that are not equal to 1, then it becomes more complicated because it's not just the power. If this were 1 times 10 minus 6, then it'd be 6. That would be the pH, would be 6, this is hydrogen ion. But since there's a 2.7 there, we have to use a calculator. And the pH is equal to negative log of the H plus. The pH is negative log of the H plus. You don't have to have this equation memorized, then we just punch it in. The weird thing about power functions is the sig figs. This looks like 3 sig figs, but it's only 2. In power functions, anything after the decimal is significant. Anything preceding the decimal is not significant. In regular concentrations, this is 2 sig figs here. There's 8.6 is not significant. But this, yeah, you don't have to do these. Those are calculations involving pH. All right. So if the pH of a solution is 8.6, 8.6 is that acidic or basic? pH of 8.6, acidic or basic? Basic. pH. It's basic. How do you reach your conclusion? Well, pH is greater than 7 are basic. They have more base, hydroxide, than acid. We could do the calculation, but pH of 5, acidic or basic? Acidic. pOH of 6. pOH of 6 means the pH has got to be 8. If the pH is 8, then it's got to be basic. So those are the types of calculations I encounter for that. So that's about it for chapter 17. We'll go back and look at some of the problems from chapter 17 later, but chapter 18 deals with chemical equilibrium. This is a chemical equilibrium. A chemical equilibrium is where we have, the chord and the reaction. One side's going to be favored. One side's going to be downhill. In this case, to the left of downhill. But sometimes we're interested in how much uphill reaction we have that takes place. This is chemical equilibrium. Chemical equilibrium is going to be defined by the equilibrium constant. The equilibrium constant is going to tell us the ratio of product to reactant, so we can see which side is downhill. The downhill side is going to have the favored concentration there. And so we need a reaction that goes both ways. It's not to say that both ways are favored, equally. One way could be heavily favored versus the other. So here's an example of chemical equilibrium. We have forward reaction, reverse reaction. And then we got to figure out which way is the downhill. Is it this way or that way? The forward or the reverse. This particular slide you don't have to worry about. It's confusing. Closed systems, all these are closed systems. But what we have to worry about is the dynamic equilibrium. Again, this is a dynamic equilibrium because the collisions never stop. It's just reached a steady level, hydronium and hydroxide, and that's about 4 parts out of a billion. All right, so this is what we call an equilibrium reaction. Equilibrium is going to tell us the balance between product and reactant. The other part of this chapter should have been divided into 2. The other part of this chapter talks about kinetics, the speed of the reaction. And so we talked about kinetics and equilibrium in this particular chapter. Well, the speed is going to depend on how many. What's the population? I said 4 out of a billion, but the actual population of molecules with enough energy is greater than 4. We need 2 things to happen. And so this is looking at the collision. This is called collision theory. The two things, one, we have to have the right amount of energy. And so if these don't have enough energy to react, they're just going to bounce off one another. And the way we could show that is by looking at something called a reaction profile. The reaction profile looks like this. So we have an H2O reacting with an H2O. Let's lower an energy here. And then there's going to be a collision. A violent collision, and then we'll have our product here. Our product is going to be H3O plus and OH minus here. This is uphill. So when we're looking at the equilibrium part, we're just looking at the final and the initial. In the kinetics part, we look at in between here. And so in order to have this successful collision, we end up generating something called a transition state here. The transition state is going to be a state that's going to look something like this. It's a state where we have a bond that's going to be forming here between the oxygen and the hydrogen, and a bond that's going to be breaking here between the hydrogen and the oxygen here. And so this would be the transition state. The transition state's not actually isolated. That is, it's this transitory state where we have bond forming. And over here we have bond breaking. And so it's this unstable transitory state. That would be this. And then, if we have enough energy, and we have the right, what we call orientation, then we should get the product. The product of this is going to be the hydronium ion and the hydroxide ion. If we don't have enough energy, then we can't make it up to the transition state. So if we don't have enough energy, we'll bounce off and then fall back down. We have to make it all the way to the top of the hill. But not only do we have to make it to the top of the hill, so we need this amount of energy. How much does it cost to climb that hill? The amount of energy it costs to climb that hill is called E sub A. E sub A is the activation energy. That's the amount of energy that's required to make that transition state over there. Or it's just the cutoff energy. The other thing we need is orientation. We have to have the proper orientation. So for example, if the water molecules were misoriented, that is, this oxygen ends up colliding with another oxygen, then even if they have enough energy, nothing's going to happen here. We aren't going to form a hydronium and hydroxide. Or alternatively, let's say the hydrogen collides with a hydrogen. If a hydrogen collides with a hydrogen, this is not going to work either. And so these orientations are bad. This would be a good orientation here because then we can generate that transition state. So I told you the population were 4. Actually, the population of molecules that have greater energy than E sub A, this would be our E sub A, is more than 4. We have greater than 4 here. We have greater than 4, but only about 4 react because the other ones are going to have improper orientation. And so for collision to be successful, that is, for a reaction to happen, we need enough kinetic energy and we have to have the proper orientation for that. Here's a slide just showing that here. The top, we have good orientation and good energy, so we have reaction. We see the transition state here. The transition state showing bond formation and bond breakage. And then we have the product here. Over here, this incorrect orientation, this looks like it has enough energy, or maybe it doesn't. doesn't have enough. Through maybe a combination, but they end up bouncing off each other. The same thing here, improper orientation. We talked about the transition state. This is a reaction profile, but this is a downhill overall. And so this is going from A2B2 to 2AB. This is downhill. However, it doesn't go straight downhill. There's going to be an activation barrier here. So what we have to do is we have to have enough molecules to climb up to the top. So this is showing the collision here. The collision's got to have the right orientation and the right energy. It has the right orientation and the right energy to make it to the top here to create a transition state. And that transition state can break apart into our product here. Overall, this is a downhill reaction, but initially there's this uphill part. Can slow things down. How can we speed up the reaction? Well, this is just showing we need enough energy to climb over the hill. This is not enough energy, almost enough energy, but then it falls back. So there's no reaction. Well, there are things that we can do to influence the rate or how fast this reaction occurs. One is to change the temperature. And so at 25 degrees C, we see the blue curve, but at 75 degrees C, we see the red curve. The red curve has a much higher population versus the blue curve, which has a much lower population. A much higher population. Much higher population means greater probability for successful reaction and faster rate. And so reactions go faster at higher temperature. Here's E sub A, the activation. These are Maxwell-Boltzmann distributions here. Lower temperatures, reactions go slower. So we can change the rate of the reaction using temperature. We can also use a catalyst. Catalysts speed up the reactions by providing an alternate path. So for example, here, the normal path is red, but if you add a catalyst, there's an easier path that can follow. This easier path means just less energy is required. If less energy is required, it shifts the activation energy in the Maxwell-Boltzmann distribution. So without a catalyst, the minimum energy is here. With a catalyst, it's easier. It doesn't require as much energy, therefore the population is going to be much higher. Therefore, the rate of the reaction is going to be much faster in a catalyzed reaction than an uncatalyzed reaction. Yeah. The other thing that can impact it is by concentration. The higher the concentration, the more collisions. The more collisions, the faster it happens. So at high concentrations, things react faster than at low concentration. This shows the development of the chemical equilibrium. Initially, we just had the forward reaction occur. And so the forward reaction occurs as it climbs up the hill. It's not until we populate the other side that we can get the reverse reaction to occur. And so the greater the concentration of products, the more the reverse reaction occurs, and eventually it will become out balanced. So for every 4 that go up, there are 4 that go down. When we reach the state of dynamic equilibrium, this is achievement equilibrium. That is initially there's one change here. And here. That graph is not that crucial. The Le Chatelet's principle is important for upsetting equilibriums. So once we establish this equilibrium, we can upset it by adding some more hydronium. If we add hydronium to this, then it's going to increase the rate of the reverse. If we add more hydroxide, it increases the rate of the reverse. And when that happens, we establish a new equilibrium. So So Le Chatelier's, what essentially we do here is we perturb the existing equilibrium and watch it shift. So here's an equilibrium reaction. I don't know if it's uphill or downhill, but let's say it's reached equilibrium. Let's say this is, well, downhill. And so what happens is these react, they go downhill, but these ones don't all stay downhill. There's going to be a small population downhill that can make it back up the hill, just due to the collision. But what we can do is, once we let this establish equilibrium, we're going to get a balance. That balance is going to be given by K. I don't know what K is for this. K is going to be the product concentrations over the reactant concentration. But we can upset that balance by increasing. Like say, for example, if we increase the H2S concentration here, that's going to be more forward reaction occurs, and it shifts it to the right. If we increase the H2 concentration here, this product, that means we're going to have more reverse reaction occur. There's going to be more collisions, and we shift it back to the left. And so this is just showing the shifts. So if we increase the amount of reactant, we're going to get more collisions. It's going to increase the forward. If we increase the H2S, more collisions, it increases the forward. If we increase the H2 is a product, there's going to be more collisions on the product side, which is going to increase the reverse reaction here. And so we'll look at some Le Chatelier's examples here. We can change the concentrations by changing the volume. The volume occupied by the equilibrium, SiF4, silicon tetrafluoride, and water yields silicon dioxide plus HF, is reduced. If the volume is reduced, it's going to impact one side more than the other. If you look at the left side, there are 3 moles of gas. 1 SiF4 and 2 H2O gas. On the right side, there are 4 moles of gas. And so if we reduce it, 4 moles of gas takes up more volume than 3 moles of gas. And so the side that's favored is the side with fewer moles of gas. If we increase the volume, that's going to favor the side with more moles of gas. And so here the volume is reduced, it's going to shift this to the left. Predict the direction of the shift in the position of the equilibrium. So the shift is in the reverse direction here. They say molecules change from 4 on the right to 3 on the left. That's molecules of gas. We ignore solid. SiO2 is a solid. Ignore that. Temperature can impact K. Temperature actually changes K. And so increasing temperature favors the endothermic, decreasing temperature favors the exothermic direction. And so in this particular reaction, it's exothermic. Heat is a product. And so if it's exothermic, then decreasing heat shifts this to the right. Increasing heat shifts it to the left. Heat is just a product in this case. And so at lower temperature, we have N2O4 and NO2s. So I count 2 NO2s and 3 NO2s. And 1, 2, 3, 4, 5, and 2O4. At higher temperature means more heat. We should shift this to the left. And you can see if we shift it to the left, we're going to form a lot more NO2s. So there are a lot more NO2s here. 1, 2, 3, 4, 5, 6, 7 NO2s, only 3 N2O4. So there's a shift there in that equilibrium. Here, this is endothermic. So if we add heat, it should shift it to the right. If we remove heat, it should shift it to the left. Predict the direction this equilibrium will shift if the temperature is reduced. So removing heat, it's going to shift it to the left. Reverse. the shift. Reduction in temperature is interpreted as removal of heat. right, this is the equilibrium constant K. The ratio is a little bit more complicated than what I told you. But no matter how we do this, we always end up with the same ratio, product to reactant. And so we could start off with all reactants and no product. Or we could start off with all product and no reactant. And we can change that amount. Or we can change the amount of reactant. But no matter what we do as our starting, we always end up with the same ratio. Okay. So the same thing here. No matter what we do to this, we're always going to end up with the same K. So we can increase hydronium, decrease hydronium, increase hydroxide, decrease hydroxide. We're still going to end up with the same K. And so these are called equilibrium constant calculations or equilibrium calculations. We're not going to get into equilibrium calculations here. This is the equilibrium constant here. And the expression. And so these equilibrium calculations are primarily for Chem 1D. And so the last section of chapter 18 is skipped. All right, so let's take a look at chapter 18. What does it mean when an equilibrium is described as dynamic? Compare an equilibrium that is dynamic with one that is static. Dynamic means there's change, static means no change. These are dynamic equilibrium. Why? Because the collisions never stop. And so there's always continual change. The no change part comes from, well, it's established for some ratio. When the rate of the forward reaction is equal to the rate of the reverse reaction. It can show like this. 2 arrows. What things are equal in an equilibrium? Give an example. The rate of the forward reaction is equal to the rate of the reverse reaction. And so these are just looking at equilibrium. 6, a river flows into a lake formed by a dam. Water flows through the dam spillway as the river continues downstream. The water level of the lake is constant. Is this system at dynamic equilibrium? Yes. This would be a dynamic equilibrium because water coming in is equal to the water coming out, and therefore the lake level never changes. Although this lake has lost a lot of water, this lake may even have it doesn't look like that anymore. Okay, collision theory. Explain why molecular collision can be sufficiently energetic to cause a reaction, yet no reaction occurs as a result of that. Well, orientation, we need 2 things. We need the energy and the orientation. And so if we're missing the orientation, we're not going to get a reaction. According to the collision theory of a chemical reaction, what 2 conditions must be satisfied if a molecular collision is the result of a reaction? Energy and orientation. Sketch an energy versus reaction progress graph, which I call the reaction profile. The reaction profile just charts the reaction as we go left to right here. For an endothermic reaction, this is an endothermic reaction because overall, if we look at the products are higher in energy than reactants. So overall, this is going to consume energy. Include A, B, and C points on the vertical axis and use them for the algebraic expressions of delta E and the activation energy. So the activation energy is this, the hill that's going to be climbed. And delta E for this is just a product from the reactant. So delta E is this. So delta E. The net change in energy. But in order for that to happen, we have to go all the way up here. Then we're going to lose a little bit, come back down here. So delta E is actually a little less. What is the transition state? The transition state is this transient state where the bonds are breaking, then the bonds are forming, and it's going to be at the top of the activation hub. We're going to see the transition state. Are conditions that affect the rate of state the effect of temperature increase and the temperature decrease on the rate. If we increase the temperature, what's going to happen to the rate? If we increase the temperature, then the population of higher energy molecules is going to increase, so that's going to increase the rate. If we decrease the temperature, we decrease the rate. So that's going to decrease the population. This is based on the Maxwell-Boltzmann distribution. 16, at a given temperature, only a small fraction of the molecules in the sample has sufficient kinetic energy to engage in a chemical reaction. What is the meaning of that statement? That's based on the Maxwell-Boltzmann distribution. Suppose that two substances are brought together under conditions that cause them to react and reach equilibrium. Suppose that in another vessel, the same substances and catalysts are brought together and again at equilibrium. How are the processes like and how are they different? With the catalyst, we're going to have a lower pump. What is a catalyst? Explain how a catalyst affects the reaction rate. The catalyst provides an alternate path for reaction. Lower energy path. If we have lower energy, that's going to increase the population of molecules that have sufficient energy. Here we have some development of chemical equilibrium. Here we have Le Chatelet's principle. We'll look at Le Chatelet's principle in detail. Then we have the equilibrium constant. Equilibrium constant, we're going to skip that. It's the product of reactant ratio. Significance of value of K, we'll look at that. And equilibrium calculations, we're going to skip those. Yeah. So Le Chatelet's principle deals with system at equilibrium. So this is already at equilibrium. Consider the following system at equilibrium at 500 Kelvin. PCl3 plus Cl2 is in equilibrium with PCl5. When some chlorine is removed, so if we remove chlorine, what's going to happen is it's going to shift left to compensate for the loss of chlorine. If it shifts left, then the PCl3 concentration will go up. Consider the following system at equilibrium. N2 plus 3H2 equals 2NH3. When some ammonia is removed, so if we remove ammonia, this is going to shift right to compensate, so it's going to make more ammonia. In what direction must the reaction run? To the right. What will happen to the concentration of hydrogen? It's going to decrease as we shift this to the right. Consider the following system at equilibrium at 600 Kelvin. COCl2 is in equilibrium with ClCl2. When some COCl2 is added to the equilibrium system at constant temperature, in what direction must the reaction run? So if we add more COCl2, it's going to shift it to the right. What will happen to the concentration of Cl? The concentration of Cl should go up. Consider the following system in equilibrium at 298 Kelvin. If the volume of the equilibrium system is suddenly decreased at constant temperature, in what direction must the reaction run? So the volume is going to impact these two differently. On the left here, we have 2 moles of gas. On the right here, we have 3 moles of gas. And so bigger volumes favor more moles of gas, smaller volumes favor fewer moles of gas. If the volume is suddenly decreased, it's going to favor the side with fewer moles of gas, which is left. So this should shift left. In what direction? The reverse direction. What will happen to the number of moles of bromine? It will go down. Because as we shift that to the right, it will consume product. Considering the following system in equilibrium, if the volume of the equilibrium system is suddenly increased, in what direction? Okay, if we increase it, it's going to favor the side with more moles of gas. So over here we have 3 moles of gas, over here we have 2, so it's going to shift it to the left, the side with more moles of gas. What will happen to the number of moles of oxygen? It should increase. If we shift this reaction to the left, it should increase. So it should. Consider the following system in equilibrium at 500 Kelvin. If the temperature of the equilibrium system is suddenly increased, okay, temperature is going to favor the endothermic direction. So we're adding heat. We're adding heat, it's going to be reactant. It's going to shift it to the right. The more reactant we have, the more this shifts to the right. What will happen to the concentration of chlorine? It'll go up. It shifts right. Considering the following system at equilibrium at 698 Kelvin, if the temperature, okay, now we add, this is exothermic, so heat is a product. So if the temperature is decreased, we're removing heat. If we're removing heat, then it should shift it to the right, the product. So those are some Le Chatelier's. We'll take a look at some more. The equilibrium constant is a little bit more complicated. It's the ratio of the product concentrations over the reactant, but it's going to be raised to the power of the coefficient. So we aren't actually going to write any of those because we aren't going to do any calculations. But we should know the significance of the value of K. So 54, for the following equilibrium, K is 4.86 times 10 to the minus 5. 10 to the minus 5 is kind of small. 10 to the minus 5 means more reactant than product. Which of the following best describes the equilibrium system? The forward reaction is favored. No. If it's small, that means the reactants are favored. Product's not. And so the reverse reaction is favored, not the forward reaction. B, the reverse reaction is favored at equilibrium. That's correct. C, appreciable quantities of all species are present at equilibrium. Well, this is mostly reactant. If it were a little bit bigger, then yeah, maybe both species appreciable would be present at equilibrium. 56, acetic acid is a soluble weak acid. When placed in water, it partially ionizes and reaches equilibrium. Write the equilibrium equation for the ionization. Will the equilibrium constant be large or small? Justify your answer. So, acetic acid will partially hydrolyze water to make hydronium and acetate. It's a weak acid, so weak acid is only partially hydrolyzed. In this case, it's about 99.9% this, and about 0.1% this. So this is heavily favored. That means the reverse reaction is favored here. The reverse reaction is the downhill direction. And so hydronium, which is a strong acid, reacts with acetate. And it's going to make acetic acid and water come here. Write the equilibrium equation. Will the equilibrium constant be small or large? Okay, so this is going to be heavily biased towards reactant, so K is small. The small ratio means mostly reactant, not much product. All right, we're not going to do any calculations here. Okay, we're going to do a little bit of review though now. Are you able to draw this to the fourth shell? Yeah. In the supplement, there are some questions here regarding quantum number. So let's review some of these things here. One, what can you say about the spin quantum numbers of two electrons in the same orbital? There are two spin quantum numbers. There's plus 1/2 and minus 1/2. If you have two electrons in the same orbital, can they have the same spin? No. If they have the same spin, it would be a violation of what principle? Yeah, actually, it is the Pauli. If you have orbitals are given by the first, so if it's in the same orbital, the orbital address is N, L, and M, and the spin will be S. And so the Pauli exclusion principle says that no two electrons in the same atom can have the same set of four quantum numbers. And so what that does is it means that if you have an orbital, one spin can be up, the other spin must be down. We can't have two of the same spin in the same orbital, because that would give us the same set of four quantum numbers, and we can't have two electrons in the same atom with the same set of four quantum numbers. And so the Pauli exclusion principle tells us the max number of electrons per orbital is two. One plus 1/2, the other minus 1/2. Two, in what subshell is electron located? The subshells are S, P, D, F. And so what is this? Is that an S, P, D, F? What kind of orbital is A? Is that an S orbital? Is that a P orbital? Is it D orbital? It's an S orbital, yeah. You can tell this is a 2s orbital. When L equals 0, that's S, so this is 2s orbital. And the electron's in there with a spin of minus 1/2 spin down. B, what kind of orbital is this? D. This is a 4D orbital. Right? This is a 4D orbital. L equals 0 is an S, L equals 1 is a P, L equals 2 is a D, L equals 3 is an F. What are the N L values for electron? Okay, this is 3P, so N is 3. What is L?
Should be 1.
Yeah, this is 3, 1. 4F. That should be 4, and L should be, L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. And so this is a 4, 3 orbital. This is a 3, 1 orbital. Those are the first two numbers. What are the possible values of L in the fourth shell? In the fourth shell, we have 4S, 3D, 4P. So 4S is L equals 0. 3D is L equals 2. And 4P is L equals 1. And so 0, 1, 2 possible. How about in the 3D subshell? Well, if it's 3D, P's what L?
2.
2. Correct. What are the possible N sub L values in a P sublevel? So NLM. L is equal to 1. M is going to be,
You said N to
yeah, the N, okay, N is equal to N. L is equal to 1. M is going to equal minus 1, 0, 1. And so the possible M values here are minus 1, 0, 1. How about F?
that would go from minus 3
Yeah.
plus 3.
Minus 3 to plus 3. Yeah. All the values. 6, in the ground state of krypton, okay, this one, forget this one. It's kind of tedious. 7, construct an energy level diagram. Okay, so sodium, carbon, bromine, iron. 8, construct an atomic orbital diagram. So what's the difference between an energy level diagram and an atomic orbital diagram? What's the difference?
The atomic orbital would have you drawing them as in, like the lobes would be, but the energy levels would be low, showing the actual S that you
Yeah, well, energy level diagram is clear. These are energy level diagrams here. Atomic orbital is not so clear. You know, it could be what you're saying, or it could be these. This is what they're talking about. In an energy level diagram, they try to scale it. You know, the biggest gap here is between 1s and 2s, and then a smaller gap here between 2s and 2p. So the first shell, second shell, third shell, fourth shell. Fourth shell is missing the 4p here. But when we look at the atomic orbital diagram, it's not clearly delineated. The gaps are all the same here. And which ones are the shells aren't so clear here. So we lose a little bit of information. The most information is in the energy level diagram. And then the next most information will be the atomic orbital diagram. This is an orbital box diagram like this. And then the least information is by this electron configuration. Electron configurations, we're losing information about the spins. So how many, actually, also how many unpaired electrons there are. So we could do some questions with the periodic table. The third period element with 6 electrons in its outermost principal energy level. Third period is third shell. Might have 6 valence electrons in the third shell. That would be the fourth shell.
Oh,
Yeah. The first shell is this, the second shell is this, third shell would be the third row here. So it would be sulfur. The third period element with 3 unpaired electrons. Phosphorus is correct. 3 unpaired electrons. A fourth period element with a half-filled D sublevel. So that would be the fourth shell. There are 2 of them. So the fourth shell would be here. We start off with 4s1, 4s2, 3d. 1, 2, 3, 4, 5. So manganese would be 1. Would be argon, 4s2, 3d, 5. That would be half filled. What's the other one? Chromium. Yeah, chromium is weird because it's 4s1, and then one of the s electrons gets promoted to the d, and it makes it half filled. So chromium and manganese would be the 2. 4, a transition element containing completely filled 4d subshell. There are 2 of them. Okay, this would be 3d. Zinc would be filled 3d. But they're asking for 4d, which would be the next one here. And then it would be cadmium. Cadmium would be completely filled because cadmium would be krypton. 1, 2, 3, 4, 5. 5s2, 40, 10. 40, 10 would be filled. But the other one would be silver. Because what happens in silver is 1 electron short. So it would be 5s1, 40, 10. That would be silver. Yeah, similar to chromium. Exactly. It'd be an exception. But I think they're only asking for 1. So that would be it. 5, an element with a half-filled 4p sublevel subshell of the same thing, or orbital. What has a half-filled 4p or set of orbitals? What is it? Arsenic is correct. 6, an element whose atoms have one of their 4p orbitals. Let's skip that one. 7, an element whose atoms have a half-filled second shell. Let's skip that. Skip these. 9, the halogen with the smallest atomic radius. That one we should do. The halogens begin with fluorine, not hydrogen. Fluorine, chlorine, bromine, iodine. Yeah, this is radioactive. Which one of these is smallest? Yeah, fluorine. So that's the halogen with the smallest radius. 10, the largest element whose electron let's forget that one. Whose electron ends in P4. Well, I guess we could do that one. This would be P1, P2, P3, P4. So which one of these is the biggest? Polonium would be correct. It's radioactive, you could say. Skip that. 12, the period 4 element with the highest first ionization energy. So period 4 would be the 4th shell. Which one of these will be hardest to ionize? Well, ionization energy is going to be dependent on size. So in the 4th shell here, which one of these is the smallest? The smallest one will be the hardest one to ionize. Yeah. So would it be potassium or would it be krypton? Krypton, right? The size decreases. Plus krypton is noble gas. Noble gases are hard to ionize. So krypton's can be one. 13, the group 2 element with the lowest ionization. The lowest ionization means easy. cyanide. That should be the biggest. So if we look at group 2, which is the biggest group 2 element? Radium? Yeah, radium, but radium is radioactive, so we're just going to go with barium. That's the biggest. It should be the easiest cyanide. There's some other practice problems. X is the element with the lowest ionization energy. So which one of these boxes will be the lowest ionization? Well, that's going to be the biggest atom. Which box is the biggest atom?
Lower left.
Lower left. So X goes here. Y is the most reactive nonmetal in this table. Well, on the left of the metals, on the right of the nonmetals, which one is the most reactive nonmetal?
Small.
The smallest, but helium's the smallest. But it's not very reactive. It would be the smallest that's reactive. None of the noble gases, so this would be helium, neon, argon. It would have to be fluorine. Fluorine's smaller than chlorine. So fluorine's going to be the most reactive, so Y goes here. Q has only one proton in its nucleus. What has only one proton in its nucleus? Hydrogen. So Q goes here. R and T have 8 electrons in their outermost. So R and T have an octet. So it's got to be one of these two here, neon or argon. Both of those have an octet. The T atom is larger. So neon or argon, which one's bigger?
Argon.
Argon's bigger. Etc. Some of these aren't so important, but you get an idea of it. So do we get a secret message out of that? Let's see. Do we get to look at the answer key? And see if there's some secret message. Do you see some secret message from all the letters? I don't know. Maybe. But it's more random. Anyway, I think we're out of time, so we'll stop. Tomorrow, I'm not going to talk. We're just going to go straight into the lab and start working. If you have any questions, I'll hang out. I'll have to start.